Suppose there's a couple, Alice and Bob wants to send a text message to Alice. How will he ensure that the text he sends will be received on time and whether it would be correct without any errors? To do this, let's use a method Shannon devised. It's passing a message through a medium which contains an encoder and a decoder. So, what does an encoder do? An encoder breaks down the message into a simpler format, maybe converting text messages into a series of bits. It also adds some duplicate bits to it, which is called redundancy, which helps in preventing lossy data. Our medium will also have some noise in it. So what noise does is it flips the bits, making zeros to ones and ones to zeros, and causing errors in the data transmission. So what's the channel capacity? It can be defined as the maximum amount of information that can be transmitted and fully recovered in the channel. R is defined as the transmission rate of the system, which is nothing but the rate of bits that can be transferred in a medium. We know that the more redundancy we add, the more better the chance of getting high quality and error-free data. But this comes at the expense of increasing the transmission rate. So what does Shannon's theorem state? It states that if you have a channel of capacity C and a transmission rate R, for some word which has a really large length of n, there exists an encoder and a decoder that will allow us to send our message at some rate r dash, such that it's greater than or equal to r, and the probability of error is less than or equal to some epsilon, which is nothing but an arbitrarily small value. So what will this accomplish? This ensures that we can send information at rates less than the channel capacity. And this way we can design an encoder and a decoder that ensures that our error probability is minimal and is close to zero. So this is how Bob's problem is solved. As long as his network provides a high channel capacity, his messages are delivered very fast. And as long as they use a proper encoder and a decoder, we can ensure that Alice receives the right message. In this video, we will prove the transmission rate R of a channel, which has PB as the probability of error. First, we'll go through the prerequisites required for the proof, and then we'll prove the theorem.
I'm Abdullah. I'm here to explain the mathematical prerequisites of Shannon's channel coding theorem, which are required for understanding the proof. The first topic for discussion is rate. Rate is given by the mathematical formula K by N. Wondering what is K and N? I'm here to explain what is K and N. K is length of source message and N is length of code word by adding the redundant bits to the source message by encoder to ensure error added via channel is either corrected at the receiving end or at least detected. So, taking the example of optical fiber, there are some impurities in the optical fiber. These impurities will sometimes add some error to the message. So, there is a need of redundant bit so that at the decoder or the receiving end, the decoder understands that there is an error in the message. So it can either correct the message or at least detect that there is an error in the message. The other mathematical prerequisite required to understand Shannon's channel coding theorem proof is typicality and observed surprise value. We are given a sequence X. It will be typical if it is likely to give X with respect to a probability distribution Px. That means we are not surprised to see X as a result of drawing from a random variable capital X. Conversely, we are surprised and it's not very typical to see X if X is not very likely to be the result of drawing from random variable X. Now, I will show you the observed surprise value mathematical formula. It is represented by capital H and it's with respect to probability distribution Px. So here's the mathematical formula of observed surprise value. Here, the capital X is a random variable over an alphabet with distribution Px, and the N is the number of times X is tried to be drawn from random variable X independently. Now it's time to understand the formula of typical. Previously, I showed you the mathematical formula of observed surprise value because it was the prerequisite to the typicality formula, because typicality formula do contain the observed surprise value. So there was a need to understand what observed surprise value actually is. So here's the formula of a typical. X is typical with respect to probability distribution P to tolerance beta if. Now wondering what beta is? Beta is just a tolerance and its value should be greater than or equal to 0. Now we know that this h is of observed surprise value. What about this h? This h is nothing but entropy. And entropy in coding theory or information theory is the uncertainty with which a random variable gives outcome. Now we are extending the concepts learned for typicality and observed surprise value to joint distributions. So the definitions would be same, but in terms of joint distribution with the two random variables having two probability distribution, px and py, such that x is typical to tolerance beta with respect to px and y is typical to tolerance beta with respect to py. Hence, joint observed surprisal value is here also we gave the joint observed surprisal value before the typicality because the typicality has the term joint observed surprisal value. Similarly, for a pair of x and y jointly typical with respect to joint distribution pxy to tolerance beta is this formula. Here the other h is entropy and the beta is tolerance. And as we know, its value should be greater than equal to 0. Now Ashish will give the proof for Shannon's channel coding theorem for the prerequisites I have shown.
Hi, my name is Ashish and I'm going to walk you through the Shannon theorem proof. So today we are going to be proving that R of PV is equal to C by 1 minus H of PV, where R is the maximum achievable rate of a channel and PV is the bit error probability, H of PV is the binary entropy function, and C is the capacity of the channel. To prove this, we will use the proof from Kramer and Fur as a given. That states that PV is equal to H of S given Yn by K. Here, K is the length of the code word and H of S given Yn is the typicality of S given the receive word was Yn. Now let us get started with the actual proof. Let Yn be the channel output and S be the alphabet and Xn be the channel input. Now, joint typicality of Xn, Yn and S is given as typicality of X of n minus 1, Y of n minus 1 and S. Typicality of Xn given joint typicality of X of n minus 1, Y of n minus 1 and S. Typicality of Yn given joint typicality of X of n minus 1, Y of n minus 1 and S. This follows from chain rule. We can also write it as equal to joint typicality of X of n, Y of n and S. This follows from the fact that Xn is known if the other symbols and the original message are known. We do assume here that every message has a unique code word and that every code word is used only once, and the block code is known. Also, since Yn only depends on Xn, repeating this procedure further, we will eventually get joint typicality of Xn, Yn and S is equal to typicality of S plus summation of I is equal to 1 to n typicality of Yi given Xn. If we know the original message, we'll know the set of code words, so now we can write the mutual information between the original message and the channel output as I of S Yn is equal to typicality of S plus typicality of Yn minus typicality of Yns, which is equal to typicality of Yn minus summation of I is equal to 1 to n typicality of Yi given Xi. This follows from the equation we proved in the previous slide, which should be less than or equal to I is equal to 1 to n H of Yi given H of Yi given Xi, which is equal to I is equal to 1 to n mutual information of Yi Xi, which should be less than or equal to NC, which is equal to NK by R. Using our lemma and assuming the bit in our message are uniformly distributed, we can write H of PB is greater than or equal to H of S given Yn by K, which is equal to H of S minus the mutual information of S and Yn as proved in the previous slide by K, which should be greater than or equal to K minus NK by R by K, which is also proved in the previous slide, which is equal to 1 minus E by R. Now we can rewrite this whole thing as R is less than or equal to C by 1 minus H of PB. Hence prove that R of PB is the maximum achievable rate for this channel. That is, reliably, this is the rate at which the data can be transmitted through this channel. Thank you guys for watching the video.